Okay, welcome everyone to the Computer Club's March meeting. I'm Phil Sorrentino, the Computer Club Secretary, and tonight we're going to discuss the technologies that make the smartphone smart. We'll be reviewing the confluence of the technologies that had to be available for the invention of the smartphone. Actually, it was the iPhone in 2007. So we'll get to our speaker in a minute, but first let me just make a few comments. Our monthly meetings are now held on the second Wednesday of the month, 7 o'clock, as you know, because you're here. Typically they're from 7 to 8. Last month we explored mission planning for drone flights. And next month the subject will be home automation with an emphasis on cameras. Also, membership renewals for 2021 can be done remotely from your own computer. Makes it really easy. Just go to our website, sccomputerclub.org, select membership, and then scroll down to the bottom where you'll see renew membership. For more details, just check page 2 in the journal. And for those of you who are in Sun City, the lab is open. It's open from 12:30 to 4:30 every day except Sunday, and social distancing and masks are still required. There are no classes scheduled for March, but there are 2 classes scheduled for April, so you can find that in the April journal. And finally, during the presentation, please submit your questions as you think of them using the chat feature, and we'll try to either answer them in real time or hold them all till the end and then answer them all together. So now for tonight's presentation, it's amazing to think of all the technologies that had to be available for the invention of the smartphone. And as a fallout, all the technologies that were replaced by the smartphone. Bill Crowe, our speaker, is a member of the Sarasota Technology Users Group and has been involved in computers during his work life at IBM and now his retired life in Sarasota as a member of the Sarasota Technology Users Group. So here's Bill to present the technology magic of the smartphone. All yours, Bill.
Good afternoon, everybody. How are you? It's actually good evening, I guess. Good evening. Coming to you in the background, you'll see a semiconductor manufacturing facility, which we'll talk about a little later in the presentation. For right now, what I'd like to do is share my screen. And hopefully everybody's now looking at the magic of the smartphones. Okay? Technology in our smartphone, and I'm asking this question more as a background, what would people say if someone in 1950 pulled out a smartphone and do it with things that we all know they're capable of doing today? Our smartphones are a wonder. Some people might even think they're magic devices. To produce them, though, required a confluence of many different technologies. What follows is an overview of the many advances and innovations that needed to happen in order for us to carry around this little thing called a phone or a smartphone. And in this case, I'm talking about all the Androids and all the iPhones and any other manufacturer of the phones that might be out there, right? Well, first of all, what has that iPhone or that smartphone replaced? And you have to forgive me, I have iPhones and I teach people how to use iPhones. This also applies to Androids, but I may slip up there, okay? You'll notice we got a boombox, been replaced by a smartphone, speakers, microphones, music playing. It's replaced a video camera, a tape recorder, a walkie-talkie, soundboards, keyboards, DVD players, calculators, computers even. In most cases, when I teach a lot of classes, they said, well, why should I get a computer anymore? And my answer is, well, if you're doing a lot of document preparation or working with things like Excel worksheets, you probably should have a computer. Short of that, cruising the internet, writing and receiving emails, playing games, all those things are done as well on an iPad as they are on a tablet or a smartphone as they are on a computer, right? So this one device replaced all that. It has disrupted a lot of industries. If you think back 10 years and think about the industries that existed then and what exists now, I showed you the boom box. I bet you can't find a boom box other than a Goodwill store, right? Tape recorders, cameras with a flash. Only the real enthusiasts now have a 35 millimeter camera, right? Video cameras have been replaced. Radios have been replaced. DVD, CD players, VCRs, record players, flashlights. You know, I can't tell you the number of times now, if I need a light, I think of my phone first, right? Calculators, address books. When was the last time you saw a phone address book, right? GPS and maps, right? Grumman used to sell GPS systems.
Yeah.
I doubt if they probably still trying to sell them, but they're probably pretty few. TVs, not so much, but still, if you can watch all the movies you want on an iPhone or an iPad or a tablet and a smartphone. The post office with email, right? How much mail do you get now that's personal?
Text
by slow mail, right? A watch. My son doesn't wear a watch anymore. He just pulls up his phone when he wants the time, right? Now I blew it and I went out and got a Apple Watch. But that's for another time, okay? The compass. You don't need a compass. It's on your phone, right? You don't need a calendar. It's on your phone. Oh, and I've just discovered this in a big way. You don't need your credit cards with you anymore. It's on your phone, right? You don't need a notebook, a clock, timer. My alarm clock is my phone. The weather forecast is on your, yes, you got it. Books and dictionaries. Now, I know very few people who read books on a smartphone, but they do read them on tablets all the time, right? And if you want to know the definition of a word, you pull out your phone and you say, hey, Google, what does mean? Yeah. Games, right? Newspapers. A lot of people have just said, hey, I'm just going to use my phone or my tablet to get the newspaper, right? Musical tuners. I dabble in making Native American flutes, and I use the phone to tune the flutes.
Oh, I remember that.
Right? And Apple just came out with Google's had one for quite a while, but Apple just came out with a translator where you can talk to your phone in one language and it responds in the other. And you don't need to tell the phone in advance what language you're talking. It figures it out, does the conversion, and gives you back the translation. Right? There's been many advances, and here's the ones I want to focus on. Development and advances in the internet. Would that exist? I mean, would the phone exist without that? I don't think so, right? Use of different bands of radio. Radio waves are used extensively on your smartphones, right? In fact, with 5G, they entered a whole new bandwidth, right? So the development of that technology, if it weren't for that, you wouldn't have a smartphone. And here's one you might not even think about: large computers on the internet, right? When you do a Google search, there's a large computer involved in that Google search. When you send an email, there's a large computer involved in that search or in that email. Large capacity data storage. Well, that's where Wikipedia and Google store all their information, right? The screen technology, the density of the pixels, which makes our beautiful pictures, and the touch technology. Man, here's one I want to spend some time on, the semiconductor development, which in some cases has made all the other things possible, right? Speaker development. You know, when you hear the sound on that smartphone, it's not bad.
True.
When you think about the size of the speaker, it's not a woofer or subwoofer, but it's pretty good, right? The camera technology, it certainly rivals a lot of 35 millimeter phone cameras. The battery development, they keep continuing to develop the battery life and the size of the battery to keep being able to make our devices smaller. Speech recognition.
Yeah.
Let's see, we've got Siri, we've got Alexa, and we've got Google.
Google Home.
Google Home, okay. We've got fingerprint readers and facial recognition software, right? And we've got that little itty bitty teeny light on that phone. And we also have light sensors on that phone that can determine whether it's in a dark room or a light room. So let's spend some time on each one of those a little bit. What is the internet, right? The internet is a wider network that allows computer networks around the world to run by companies, governments, universities, and others to all talk to one another. So that's what the internet is. The World Wide Web is not the internet. They're two different things. The development of the World Wide Web began in 1989. It is the process by which information can be accessed and shared across the internet. The internet is the enabler because it's got everything connected. The World Wide Web is what makes the information, everybody operate under the same ground rules or the same language. Okay? Internet's the connector, the web is the controller. That's what the internet looks like, right? Everybody's connected. Versus the World Wide Web is the HTTP : / all those things we used to have to put in.
Yeah, right.
Right?
Not as much.
Your phone has many antennas in it. So now let's talk about that, right? The radio waves, right? Connecting it to GPS, the satellites. Cell phone towers. And there's a whole new bunch of cell phone towers that are currently being erected to handle 5G, right? But they're miles away. The GPS orbiting satellites are low Earth orbit. Wi-Fi is 100 feet or so away, right? Bluetooth is this kind of thing you use in your car, for example, or you use to attach your headphones wirelessly to your smartphones, and one thing called near field communications. And that allows you to use your phone as a wallet. So you can actually take your phone, bring up the particular application, just wipe your phone over the reader instead of swiping a card in it. Okay? The speed of the internet, right, has gone from 1G, 2G, 3G, 4G, and now we're on the verge of a booming 5G, right? 5G is about 20 times faster than 4G. And I got a little comparison here. 3G was deployed in 2004, 2005. 4G was 6 to 10, and 5G has just started in big time this year. Right? The bandwidths it uses. This goes 2 million bits per second, or 2 million, 200 million bits per second, and greater than 1 gigabit per second. So that's 1 billion bits per second it's transmitting. The latency is how long it takes the signal to get to you. right? And it's the delay in which you request something and it responds. And it's gone from, now these seem like awful small numbers to start with, right? It's gone from 10 to 100 milliseconds to 20 to 30 milliseconds to less than 10.
That's fast.
Okay. When I was working at IBM, when we had these terminals, that latency was important because we'd push a button and the signal would go back to mothership, and then it would process a while and come back. And it was a second or two. And that was slowing in your process of trying to get something done when you type a word and it takes that long for the letters to show up on the screen. Okay. Average speed, 144 kilobits per second, 25 million bits per second, and 200 to 400 million bits per second. So that's what we're going to see. And by the way, they're working on 6G now, which is another order of magnitude above 5G. Okay. If you look at the large scale computers that are out there, right? They're used by smartphones. What are they used for? That Google search. Things like Google, Bing, Yahoo, and DuckDuckGo. Okay, give you some examples of the number of searches that are done and have to be processed by those large computers. Google alone processes about 3.5 billion searches a day, right? Siri, Alexis, Cortana, and Google, right? How many times do they get asked questions, right? And did you ever think about what happens when you, what time is it, Google, Alexa, or what time is it, Siri? It has to take your voice, convert your voice to digital, do the digital search to try to find an answer, generate the answer, convert it back to a voice, and give it to you. And it does all that not on your device, but it does it in one of the large computer systems. Okay. 157 million homes in the United States have smart speakers, like Alexa or Google, right?
I've got 4.
Who said that? You did, Fred? You said that, Phil? 4?
I've got 4 of them, yeah. One in each room and one in the garage.
Okay. Emailing, Google, Yahoo, Comcast. That's 246 billion emails a day are being processed, right? Stock market. Ooh, 58 billion stocks are traded in one day. Streaming videos like YouTube or music from Pandora. This one blew my mind. 300 hours of video are uploaded to YouTube almost every minute. Almost 5 billion videos are watched on YouTube every single day.
Wow.
None of this would be possible on your smartphone unless they were there, right? Facial recognition. I'm going to pause here and just tell you a little story. In China, this BBC reporter went to one of China's larger cities that had the most attached cameras any city in the world. And the BBC reporter went into the local police station and he said, "I want you to mark me as a criminal that I need to be captured and take my picture." The train station was 3 blocks away. He walked out of the police terminal, and before he got to the train station, he was under arrest because of facial recognition, right? Now that's good and bad. Just think about that a while. That's for another day. We can talk about that. right? Large capacity storage are located around the world. And on a smartphone, and on the smartphones use it. Mega, giga, tera, peta, exa, and zeta byte storage capabilities. For example, maps. They have millions of pictures taken from space. They stitch them all together, combine them with street level images that Google has, and collected with thousands of vehicles traveling around the world. Google Images gives you, anybody ever play with Google Images? You go to Google, and instead of looking at just a Google search, you say, I want images. And they have billions of pictures. You type in any subject, you get all kinds of pictures. Email providers use mass storage facilities to house all the email that's needed, right? Cloud storage, you've all heard of the Google Cloud, the Dropbox, the Apple iCloud, right? Every email you send has to be stored in some cloud somewhere for you to be able to access it. So let's switch gears, right? We all pick up our devices and we just love that touch and that feel and that nice feeling you get when you move your finger over the screen and it responds instantly. Two technologies were combined to be able to control the screens. One is the touch screen and the other is the display quality, right? So I'm going to let this person describe that. And Phil, I need you to shake your head if you're getting a good volume.
Touch screens are everywhere, not just in smartphones, but in supermarkets, ATMs, and even airplane seats. And you may have noticed that not all touch screens are the same. The old school touch screens can be pretty tough to use. Sometimes it feels more like a push really hard screen instead of a touch screen. On the other hand, certain smartphones and computer monitors are really responsive to many different touch patterns. There are lots of different technologies out there, but they're all trying to achieve the same goal, sending precise electrical signals from specific locations on the screen. One of the most widely used types is resistive touchscreen, where you have to physically push and bend the screen to make it work. Resistive touchscreens are made of two separate layers. The top layer is made from a flexible, transparent material such as polyethylene, which is a common plastic used to make things like soda bottles. And the bottom layer is made of something more rigid, like a sheet of glass. To make the screen work, both of these layers are thinly coated with some sort of metal compound that conducts electricity, like indium tin oxide, which is commonly used because it's transparent. These layers are also separated by tiny insulating dots called spacers, which don't conduct electricity. They keep the screens apart to make sure there aren't any false touch signals. When the screen is on, a small voltage is applied across the screen in both horizontal and vertical directions. As soon as you push down on the flexible screen with anything, like your finger or a stylus, it connects the two layers together. This changes the voltage, and a small processor connected to the screen can calculate exactly where you pressed in X and Y coordinates. These resistive touch screens are pretty affordable and durable, so they're used for things like credit card readers in grocery stores where you need to capture touch data of a messy signature over and over again. But they can be a little frustrating to use if you don't push hard enough. Plus, they normally can't understand multiple touches at the same time, so they're no good for two-finger zoom or more complex tasks. That's why these days, most smartphones rely on capacitive touchscreens, where your finger becomes a key part of the electronics. There are different kinds of capacitive touchscreens, and they can vary from device to device. But one basic design is a sheet of glass containing a grid of hair-thin lines of a conductive metal, like indium tin oxide. The grid lines in one direction are called the driving lines, which provide a constant electric current, and the lines in the other direction are called the sensing lines and detect this electric current. At every point where the sensing lines and driving lines cross, there's a specific electrostatic field, which is registered as neutral by the processor in your smartphone or computer. But that all changes when something conductive comes along and touches it, like your finger. See, the human body has a natural capacitance, which means our bodies can conduct electric current and can store electric charge. So when your finger touches the screen, the charge in the screen is drawn around that point, distorting the electrostatic field. The electricity doesn't actually flow through your finger. The electrostatic field feels the effects of your electric charge and redistributes itself accordingly. Even really small changes are detected by the processor, which can then interpret the patterns you're making, whether it's a tap or a slide. Because the lines of the grid are so thin, capacitive touchscreens are super accurate, and some versions can process multiple touches at a time. But they won't work if you have gloves on, because the cloth isn't conductive, unless your gloves have those special fingertips with metal fibers inside. Plus, something like sweat can affect how electricity is conducted across the screen, because it's full of salts. It's all about the materials that can affect the electrostatic field generated inside your screen. So the next time you're texting on a smartphone or scrolling through internet forums on a tablet, just remember you're actually a part of the electronics that make it work. Thank you.
Mm-hmm.
Okay.
Yeah, interesting.
Interesting little facts. But again, remember, the point of this thing is that we wouldn't have smartphones without all that technology, right? As far as the display quality goes, that's controlled by pixels, right? The number of little dots that are on there. And every time we get a new smartphone, they've usually have increased the number of pixels on the display, right? The first smartphones had 160 pixels in one direction and 923 in the other, right? In 2001, they went to 256 colors.
Yeah.
And in 2007, the pixel count went to 320 from 160 and 480 from 293, or 153,000 pixels on your phone, 153,000. Now that's pretty good till you look at today, right? Today's pixel count is 1920 by 180 for full HD, and that's over 2 million pixels on that little phone. And that's why the quality of the pictures are so good, right? Let's talk about semiconductor. I'm in a semiconductor lab. You can see that behind me, right?
Yeah.
Nobody believes me, Phil. I don't understand it. The semiconductor is one of the founding building blocks of many of the technology advances we are seeing in our phones. Almost every one of the things I've shown you and will show you required the semiconductor industry. Storage capacity, processor speed, internet speed, camera technology, screen technology, all would not exist without the advances we've seen in the semiconductor world. So I wanted to spend a little bit of time explaining what that is to you. Okay, not to confuse you, just to give you an idea of what's happening. What is it? What's its history? What does it take to make a semiconductor? How do they do it? It takes lots of money, first of all, to make a semiconductor. Are made from materials that have been conducted between wait a minute, let me go back to that. Semiconductors are materials which have conductivity between conductors, generally metals, and non-conductors or insulators, such as most ceramics. Semiconductors are used to build electric circuits. The trend, right, in the 1950s, there was a drastic reduction in the size of electronic devices when it has moved in a rapid pace since 1950. As a result, the speed increases. As you make the electronics smaller, the electrons have to go shorter distances, and therefore everything speeds up, right? Our iPhones can perform 2 billion additions a second.
Wow.
That particular processor that can do that is more powerful than the one that was used, that NASA used in its big computer when our astronauts went to the moon.
That's just.
Now, I didn't say we could launch an astronaut with this thing, but it can sure compute fast. Okay. The push for smaller devices allows an increase in functionality for the unit space, and it causes for faster devices. And here's a graph that goes from millimeters down to nanometers. And I have a little bit more on that, but here's where we were way back when we were making tubes, and then the semiconductor industry started. Okay. And here's the size of bacteria, clear up here. Well, bacteria is here.
Wow.
Okay, so let me just. Sesame seed is 1 millimeter. Bacteria is the next step down, 750 micrometers. The human hair is 100 micrometers. Unaided vision is 1 micrometer. Oops, sorry about that. Let me do that again. Think Corona.
Thinking about that for the last year. Pretty neat.
So what we were saying is, can human beings make something the size of 1 nanometer or 7 nanometers? And the answer to that is yes, right? 10 microns, right? 50 microns is the diameter of human hair, right? 3 microns, right? In 1977, but we were a white blood cell is 25. Large bacteria is 2 mics, right? 800 nanometers in 87, 300 nanometers in 93, 250, notice how it's slowing down a little bit, 130, 2001, the size of the coronavirus is 90. And the thing the semiconductor industry has done is says, I can make things, circuitry that's man-made, smaller than that. There's 65. I can make 165 nanometers in 2005. And if I keep going down here, right now, we're making things 10 nanometers, the size of an oxygen atom. Okay.
That's something you can do on your kitchen table.
The 7 nanometers is what they're developing. Okay. What's it take to make them? A lot of money and a lot of space, right? A very clean environment, 7 to 10 to more than that, cleaner than an operating room in a hospital. Because a small particle of dust, dirt, just destroys the device, right? It also takes a lot of time and many, many steps to make one of these things, 1 to 2 months. And as you'll see in the film, there's a development process and then there's a manufacturing process. And if you screw up the development, it takes you 2 months to make a new one, right? And a lot of different processes, right? Here's what we start with. It's called a silicon ingot. And you'll see a little bit more on that in the next video here. Okay? It looks like this, and I actually have one here. You can't see me right now, but I have one in my position. I'll show you when I come back on. And we take that silicon ingot, and it's made of sand, and we slice it up. In other words, we cut little pancakes out of the silicon, right? And we end up with something called a wafer, right? It takes 6 to 8 weeks, 6 to 8 to 15 weeks. It's a bunch of chemicals are applied, photoresist, so it's like a photo process. Lithography takes place where we transpose and make the picture onto the wafer. And then we go through a bunch of chemical processes. And we do that same thing, building up layer after layer of material until we are able to make the device. So it takes a great deal of accuracy to do this as well, right? So you start with a wafer, you make all these little things on it called chips. You might have heard the word processor or the word memory. Memory would be a chip, a processor would be a chip. And then we package it together, and it makes a carrier or a wafer, dicing, and then we put it together, and these things are called modules. So we start with a wafer, make the wafer, then we cut it up. So you've diced it up, and all the way along, you got to figure out ways to test it to make sure it's working. Then you place it on a board. You may have heard the word motherboard, and that's what's on your computer. There's a motherboard on every device. There's one in your phone. We're just used to seeing them in laptop or desktop computers. Okay? Any questions about that? No.
No, I was just wondering, Bill, what technology is typically now a current processor technology used for processors that we would buy in our laptops? You know, how small?
Okay,
how many microns?
we're probably in the 15 microns,
micron
15
area?
to 20.
Uh-huh.
The more advanced ones that are really expensive, like the ones that NVIDIA might be using in their processors for gaming computers, are 10. And the leading semiconductor manufacturing facilities are working on 7.
Wow.
Okay. And by the way, Intel's a little behind on this whole thing. Okay, they're just coming to life with 10. Okay. The camera technology. I need to check something here. Hold on. I want to play another video for you, so hold on.
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See integrated circuits in the making.
Can you raise the audio just a little?
Factories. Let our experts walk you through the nanocosmos of the atom. A world that normally remains hidden from our eyes. In the beginning is the circuit diagram. At design centers around the globe, experts collaborate to design circuit diagrams, sophisticated integrated circuits, like microprocessors, high graphic processors, and wireless communications ICs. The next step is manufacturing. The disk substrates for the microchips are made from quartz sand and are called silicon wafers. To make these wafers, a huge crystal is drawn from purified silicon melt. The result is a perfect silicon lattice into which the transistors will later be fitted. However, impurities pose a threat to these flawless silicon crystals. Our global foundries manufacturing teams must therefore take extensive precautions every time they enter our dust-free clean rooms. The result? Our wafers are fabricated in an environment that is more than 100,000 times cleaner than an operating theater. Completely free of dust, the silicon discs arrive at the clean room. Here, 25 wafers are packed into each hermetically sealed container and sent off on a journey that will take them through hundreds of manufacturing steps. Photolithographic techniques transfer the circuit structures to the wafers, rather like slide projection. The key to this whole process is a solid mastery of light. The silicon disc is spin-coated with a photosensitive resist. UV light transfers the circuit structures depicted on a mask to the wafer. The exposed parts of the resist are soluble and are removed by a developer. The transferred structures can now be used as a template. The unprotected parts of the water surface are etched away. The structures of billions of small current switches are generated on each wafer, tiny transistors. The photolithographic stage, wafers move on to the ion implantation, where the electrical properties of the transistors will be specified. Here, the engineers make good use of one of silicon's most important properties. Silicon is a semiconductor, which means that its conductivity can change via a high precision emplacement of so-called dopant atoms. First, dopant atoms are injected into the silicon structures. These atoms then distribute randomly in the silicon lattice. At high temperatures, the doping atoms become flexible and take on a fixed position in the atomic structure. The complexity of manufacturing tiny transistors requires a clean room as big as 2 soccer pitches.
Pitch.
While our people monitor the complex processes, automated manufacturing itself always takes place within hermetically sealed production lines. Copper dominates the next process step. The finest interconnect wires link up billions of separate transistors to form integrated circuits. Before that can happen, however, cleaning is essential for wafers, as particles lurk at every stage in the manufacturing process. Before the copper is poured into the trenches for the interconnects, a barrier layer is applied. It helps to avoid short circuits and guarantees reliability. The trenches are then filled with copper. Finally, the excess copper is ground down to the edges of the trenches. This insulates each interconnect from the others. A microchip made of copper wiring established GlobalFoundries as the first company in the world to adopt copper in volume production. A foundation for the state-of-the-art multi-core processors that GlobalFoundries is introducing today in all product areas. To keep us on the leading edge of the world's chip makers, electron microscopes constantly monitor every step in the manufacturing process, down to the atomic structures of each individual transistor. In 2 months, the wafer is ready. Huge integrated circuits consisting of conductors with a length of multiple kilometers link up 100 billion transistors on numerous levels. And that in a space no larger than a fingernail. GlobalFoundries, the first truly global semiconductor foundry, located in the USA and Germany, Fab 1 in Dresden, and the future Fab 2 in Malta, New York. Together, they'll be 2 of the most advanced chip factories on Earth and a testing ground for the very latest microelectronic innovations from around the globe.
How was that for semiconductors?
Fascinating.
That, I just, every time I see it, I worked there for many years and I'm still impressed by just the sheer size of which they're operating. It's just so small, it's unfathomable. The camera technology in 2018, 1 trillion pictures were taken on smartphones, 1 trillion, right? The best smartphone camera collects 16 million pixels for each picture taken, right? The human eye has 120 million light sensitive rods, which can loosely be called pixels, right? But look at what happens here. All these pieces, and you look at your phone, you see that camera, but you know all these things that are in here, and there are actually motors in there that change the depth of field to change the focus. It's an actual motor in the lens itself, right? Most smartphones have 2. That's the story on the cameras. We look at the speakers, right? All smartphones have 2 speakers. one right where your ear, which is smaller, and one at the base usually, right? And the one at the top is, here's the size of a dime, and this is an actual speaker. The other one is about the size of a dime, right?
Of these systems share a lot of commonality.
I'm going to skip that one. Okay. Battery development has been 5 times better than, even though you have to charge your phone every day, the phone does so much more compared to 5 years ago. And the battery is probably one of the limiting factors because of its size and the size it has to be. It's one of the bigger components in your smartphone.
Mhm.
And the biggest battery drains are trying to access the internet and making display. So if you don't want to use your battery life, turn off the internet, right? Silence the internet, put it in airplane mode, and or reduce the display brightness.
Turn off Bluetooth.
Turn off Bluetooth as well. The batteries we use tomorrow will weigh about the same, but we'll have about twice the energy. And we're still waiting for that big breakthrough in batteries. Speech recognition. Little story here, right? In 1962, IBM introduced a thing called Shoebox, which understood and responded to 16 words, 1962. Carnegie Mellon got that up to 1,000 words in 1970. In the 80s, the speech recognition vocabulary go from a few hundred to several thousand words, right? Oops, I'm sorry, I clicked the wrong button. Oh, there we go. Technical difficulty.
You having any engineers in the neighborhood?
Today, some of the largest tech companies are competing for the heralded speech accuracy title. In 2016, IBM received a 6.9% error rate. And Microsoft got down into 5.9, and Google is claiming 4.9% error rate. It's both relatively inexpensive and powerful. With the advancement in artificial intelligence and the increasing amount of speech data that can be easily mined, it is very possible that voice becomes the next dominant interface. And it's becoming more and more. I don't know about you folks, but I use it on my phone instead of my keyboard. So I just turn on the speaker, I turn on the microphone when I'm ready to type text, and I start speaking, and it does voice to text relatively accurately. This is an interesting, how many kids do you know that can write cursively? Well, tomorrow, they don't even be able to write. If you think about it, that's where we're heading.
Sure.
Fingerprint scanners. There's 2 different types, capacitive and ultrasonic. And I'm just going to quickly go over this. Ultrasonic is the latest fingerprint scanning technology. And that's the one you can actually put on your screen, on the screen of the smartphone. And you could actually touch the screen and get a fingerprint.
Oh.
Facial recognition. I've got one of the newer iPhones that has facial recognition on it, right? And it's pretty nice, right? I don't have to put any passwords in.
Can you have more than one person?
Phil, I know you can have more than one fingerprint. I haven't tried more than one face. So when you have fingerprint recognition, you can have more than one.
Yeah.
I'm not sure about the face, right? The facial recognition market is expected to grow to 7.7 billion in 2022. And right now there's a big debate on that. Can the police, criminal associations use facial recognition to surveil and capture criminals? And there's also a mixed message on that. They're also surveilling you then as well. Right? A picture of your face is captured on your phone. The facial recognition software reads the geometric characteristics of your face, and the result is a facial signature. The facial signature, a mathematical formula, is compared to the database of known faces to determine a make. Okay? And last but not least, LED and light sensing technology, right? Every smartphone I know now has a LED light on it that uses as a camera flash, right? It also has a light sensor. On most phones, it's near your ear, where you would put your ear, and it's sensing the light and adjusting the intensity of the screen based on the external ambient light. And if you put it up next to your phone and answering a phone call, in some cases, it will turn off the screen, knowing that it's on your ear and you're having a phone call. Okay. So why is the smartphone so magical? It's a combination of all these advances in technology in one place and has made it available literally at our fingertips. It may seem costly, but when you consider all the things that I've just shown you in one small package, it's pretty magical. Now, all that's required is for us to learn how to use it all, right? And I always have this expression, one thing at a time. Don't worry about what you don't know. Just focus on learning one thing a day. Here's a picture of an Android and a smartphone. So I'd like you all to have fun with your device, right? And did I get any questions, Bob?
No.
Good. All right. It's not that kind of presentation. Right?
You know, you did mention that there was an app for credit cards.
Yes. On the iPhone, it's called Wallet. I'm not sure what it would be on the Android.
I don't know of any. I guess that's Apple Pay and...
Well, it uses Apple Pay.
It uses, I see.
Okay?
Well,
Apple Pay technology, but it's the Wallet app.
Well, I'll take a look around. Well, I guess we've come to the end, right? You said there were no questions, Bob?
No, I haven't seen any questions. Whoa, wait a minute. Oh, we just had somebody get on right now.
Oh, a little late.
Hey,
But-
Bob, is that presentation available online?
Yes, that presentation will be available online in about an hour.
Here's what you look like if you put on one of these garbs, by the way, folks.
Yeah, to get in there.
Oh,
Wait a minute. No, the wrong way. There you go.
okay.
Is that
You
or
can get
you're...
you're completely covered. And there's actually booties you put on, gloves you put on. You go into one of these clean rooms.
And people work in those for 8 hours?
Yep.
Well, they probably work in more like 2 to 3. They take breaks.
Sessions, yeah.
And those rooms are quite chilly because these things are quite warm. Okay.
That's great.
All right. So it's
Well,
a great
okay.
COVID. It's a great COVID getup.
Yeah. Well, I guess we've come to the end, so let me just say thanks, Bill, for a very interesting and informative presentation. I think now we all know a little bit more about the technologies behind our smartphone. I hope people are encouraged to learn a little bit more about their phones and take advantage of it. That way you get to use all of that technology all at once. So just for everybody who's tuned in, don't forget the next meeting next month will be home automation. It'll be on April 14th. So good night and stay safe, and thanks again, Bill.
And if you liked what you saw tonight, please hit the subscribe button and click on the little bell for the notifications so you'll know when anything's coming up. And we'll see you next month, folks.
See you next month.
Goodbye, everybody.